Hi, my name is Sarah Snow, and welcome to Senior Design Day. Well, we're going to be going over how to design subsensory vibrating instruments. These are abstract, and we'll get into that a little more later. These are our team members, Matt Herr, Nick Patel, Becky Telly, and myself. Here's our advisor. Dr. Turkey oversaw the electrical design. Dr. Lauer helped with research designing and will be doing future lab testing. Dr. Darvish helped with biomechanical consulting. The problem that we're addressing is that impaired balance and proprioception can lead to an increased risk of falling. Now, proprioception is the ability for one to sense oneself, to its body, and its surroundings. There are many different conditions that can cause this, such as age, stroke, cerebral palsy, diabetes. Here are some statistics that show just how dramatic this problem is. In 2008, over 19,000 people died from unintentional injuries. In 2009, 2.2 million non-fatal injuries happened and were treated in emergency departments, and over 500,000 of these led to long-term hospitalization. So we're designing this for the BEPO lab, which is the Virtual Environment and Postural Orientation Laboratory. Dr. Lauer will be using it and helping with research and testing. Hopefully, the future benefits that our device will have would improve quality of life for people, aid in further research, and possibly reduce hospitalization costs. So we did a lot of reading, and the research says that applying a subsensory noise to the soles of the feet, let's see if this works. Applying a subsensory noise to the soles of the feet stimulates the mechanoreceptors and leads to improved balance. This image shows that when the noise is applied, that the center of pressure, the balance, is more centered. One of the issues that we're having right now is that most of the testing that has been done has been in laboratory and stationary. So we're trying to address this being a portable device so that it can be taken home and used by the subject. So our solution that we're coming up with and designing is designing a subsensory vibrating insole that is compact and portable, low cost, and low maintenance. Here's our hardware diagram. So it starts off with the subject taking a step, which stimulates the force sensing resistor, which puts an output voltage to the microcontroller, which is the brains behind the operation. And that transmits the data to the SD shield, and it also outputs a signal to a potentiometer, which goes to the LRAs, which are what vibrate in the insole. Here's our software design diagram. So we have five major technical design constraints. The first is vibrational accuracy. So the vibrational accuracy has to be between 100 and 250 hertz. This is because this is the vibrations that are optimal for the mechanoreceptors that we're targeting. It also must be able to function for at least 6 hours. We estimate this to be about the time active one person spends per day. It has to be efficient. We would like it to have at least 95% accuracy in detecting steps. And it should be durable. It should be able to withstand 1 to 3 times a subject's weight, according to ASTM standards. And there must be enough memory for it to store 1 month's worth of data. And our non-technical design constraints are cost. We want this to be cost-effective to manufacture. Our budget is $500. We want it to be portable, again, because it needs to be worn by the subject, so it must be compact. It should be comfortable because it's being used daily. Because it's going to be used daily, we want to increase patient compliance. So that can only be done by making it comfortable to use. The size of the components themselves must also be compact, because the insole must fit in the shoe and the actuators must fit in the insole. And safety is very, very important. We don't want anyone to get injured using this for any reason whatsoever. Here are some of our components that we'll be talking about in a minute. These are our force sensing resistors. They act as pressure sensors. They will be placed in the insole. they are what turn the device on, basically. And this is our power supply. We're using a lithium-ion backpack that's specially designed for the Arduino. It has a high capacity of 2,200 milliamp hours and is tested at 29 standby Arduino outputs. The Arduino that we are using is an Arduino Uno. It has three main functions. Sensing and reading the data from the transducer, outputting a signal to the LRAs, and storing data to the data sheet. A potentiometer seems like a really simple component, but it's actually very important. This is how the clinician will be able to turn down the amplitude of the vibration so that it is actually subsensory. Our actuators are LRAs, and the reason why we chose them is that they are discrete in size, that they take minimal power consumption compared to other actuators, and that they vibrate within the correct threshold. There's going to be 6 per person, 3 per shoe, 2 at the ball, 1 at the heel foot. And this is our SD shield. This is where we're going to do all our data logging. The material for the insole itself is cork. We chose cork because it's good hardness, it's very durable, it has minimal deformation, great thermal insulation. And now into mechanical testing. So what we did is that we ran an MTS impact testing with the full insole in a shoe. And here are the before and after results. Before it is 4.0 millimeters, and after it is 4.75, and that's actually a rather good result. Also before and after, we did vibrational testing. Here's before. Here's before, and here's after. And we got very good results again. The actuators didn't change the vibration whatsoever. We had a mean squared error of 5.5 times 10 to the negative 7. We did SolidWorks simulation. Here's our original model. And here it is after a displacement test. Now it looks like there's a lot of displacement happening towards the perimeter, but actually it's not that much, because if you look at the scale, it's times 10 to the negative 4th millimeters. So we're well within range. Here's our strain testing. Again, the strain is minimal. And this is our thermal testing, and it pretty much just demonstrates that cork is indeed an insulator. And the peak that we see in the center, that's the actuator. It's metal in this model. It's actually covered with a little bit of rubber, and we're going to cover the whole thing in leather so that the thermal conductivity isn't going to be an issue. The reason why we're concerned about thermal conductivity is because feet get sweaty and hot. So we want things to be as nice as possible for the subject. Now onto electrical testing. Here we're testing the FSR, the force sensing resistor. So the way an FSR works is pressure is inverse to the resistance. So when we have an open FSR, it is an open circuit. Resistance is infinite. And the more pressure we apply, the less resistance there is. Now we've combined it with the interface circuit. So what we did is we applied 5 volts DC to it, and and ran the 5 volts DC through it and had the voltage sensed. And when you apply pressure, so the resistance goes down and the voltage goes up. And this is important because this value is what the Arduino itself reads as the pressure sense. In terms of testing the accuracy for the linear resonant actuators, this is the serial monitor for our Arduino while we're doing these tests. So when it senses no pressure, there's no frequency deliver. When it senses a pressure, it delivers a frequency. The frequency is within the right range. And I don't know if you can really see it, but we tested the voltage across the actuators as well, and it's at 1.68, which is good because they're rated for 2. And here's a sample of our signal. Here we're trying out the step counter. So these are 3 conditions. In the first, there's no pressure sensed, no frequency, and no steps counted. Here, steps have been taken. This is post-step, so there's no pressure sensed, but there's still frequency. We have delay of about 1,000 and steps have been counted. And here we have well after a step has been taken and the frequency stops, and it's not detecting any more steps at the moment. Our SD shield. So, what we do first is we initialize the card. And when the card's ready, it makes this line of data, which is therefore followed. Now, when it goes onto the SD card, it turns into an Excel file for ease of use and definition. And it is exactly the same data, so we're having really good accuracy of transferring data. Memory. So the way that we tested memory was that we left it on for 10 minutes while testing it and measured the amount of memory it took, which was 252 kilobytes. We converted that into a month, and it came out to 1.8 gigs, which is 27.2% of the full memory. So we have a lot more capacity. It's a 4 gig card. Here's our first prototype. You can see that we have the battery pack, the Arduino, voltage integration circuit. And here's our second prototype, and probably our final one. Here we have the battery pack, the Arduino Uno, we have a breadboard shield, and we have our SD shield. Here's a better view of it, and a better view of it all together. So here we have one that's open. We've got the actuators for sensing resistor, and the one with the leather covering. A close-up of our hardware. Oh, you can see the potentiometer really well in this one. Oh, one of the reasons why we used a trimmer potentiometer is for less tampering after it's already been set. Here's our cost budget bill. We are well within our budget. So, at this point in time, what we've done is a fair amount of research. We've designed a system, and we've done some SolidWorks modeling. We were able to write well to the SD card. We've finished 2 prototypes, and we have gone through some full device testing. What we're looking forward to is the device being used in the clinical research at the Depot Lab, possible wireless integration, and an integrated circuit fabrication, because although it is pretty compact right now, it could be smaller. Any questions? Yes.
So can you go back to your data slides?
Which one?
One more. There.
Uh-huh.
Now, when you on that lower right, you say the sensor reading is 633, 634,
Uh-huh.
and then your frequency is supposed to be this related to that, right?
No, it's not. As long as it senses the pressure, it will be a frequency. The frequency itself is randomly generated between 100 and 250 hertz.
And so there's no correlation with the sensor value and the frequency.
There is not. No.
What does a frequency mean then?
The frequency was chosen in a specific range to stimulate the mechanoreceptors that are on the bottom of the foot, the ones that we're targeting.
Oh, all right. So it just picks a random frequency. That's the
Exactly.
frequency of the stimulator.
Yeah, and the reason why it's random is because it's supposed to be like a noise signal. That's supposed to be the most effective for this application.
I see.
Any more questions? Is there another application you can actually apply this?
Another application?
Yeah.
There's a lot of different applications for this. The insole, of course, is what we're working on. However, it's also been used for helping improve balance. If you put haptic motors on the chest, it's supposed to help with arm coordination, and also people who have inner ear damage when they go off balance. It can have a haptic way of telling them when they're off. But yeah, it's important because we should be doing more research on this.
What is the, like, once you apply it for 6 months or something, how do you measure your progress in that?
Okay. Well, that will be done during the clinical trials at the lab.
Yeah.
But a measurement of progress would be something like a training behavior, an adaptive behavior, where, well, the way that they measure it in the lab is I feel like I shouldn't, they put up a visual scene that either rotates or somehow disorients the subject, and that creates a sway or some kind of a postural response. And the more sway there is, the less balanced one is supposed to be. Or if there is more variation on the sway, like it's okay to have a steady sway, but if you're really off balance, it's not going to have much of a rhythm to it. So the less that these off-balance behaviors are, the more it would indicate learning, training, improvement.
So it can be measured, but of course it varies from patient to patient.
Yes, it varies greatly. And the thresholds vary greatly themselves.
Okay. Any more questions? Thank you. Okay, go ahead. So,
Oh.
no, go ahead.
Excuse me, is the intent to use this in training sessions by a therapist exclusively, or to ultimately come up with a product that people would actually wear on an ongoing basis?
Well, it's going to take a while before we can get it to a product that people can wear on a daily basis. But yes, ultimately.
In which case you probably wouldn't need all the measurements and some other stuff. You just want something that stimulates their...
Absolutely. First, we have to make sure that it works, which, is a process within itself.
And as a follow-up regarding whether it works, has it been confirmed that the cork does not so damp the vibrations that it doesn't feel?
That's a good
another
point.
reason to use it.
That's actually a very good point, because cork would damp the vibrations if it were on top of it. But instead, because it's surrounding it, the actuators are placed strategically to target the mechanoreceptors that we want to. So the fact that it isn't transferring vibration around it is actually beneficial.
Oh, so they're right up against it.
Yeah.
They're over.
They're like, the cork
They're
is
embedded in the cork?
they're
They're
embedded,
embedded
yeah.
in the cork. I see, so it focuses.
Let's
Okay.
go over. Yeah, you can see the actuators, the tops of themselves, right there. They're covered with a little bit of rubber, so they're black. And there's the leather heel liner on top of it. So, yeah. No problem. Anything else?
Okay. No more questions? Thank you.
Oh, thank you.
As a group,